All right, this is the video for to substitute for class on Friday, April the 8th. And this is covering sections 10.2 and 10.3 on bonding theories, including ligand field theory. So the LF here stands for ligand field, and this is stabilization energy. So we've been talking about magnetism and how we can develop magnetism or calculate magnetism from the number of unpaired electrons. So if we are thinking about a pure metal, say pure vanadium, all of the vanadium atoms are surrounded by other vanadium atoms that are not charged. And so all of the d orbitals have the same energy, or we say they are degenerate. So we follow Hund's rule that says we spread those electrons out. And this means we have 3 unpaired electrons. So if we're calculating magnetic moment, our spin is 3/2. So the number of unpaired electrons divided by 2. And we plug that into our formula for the magnetic moment. So 2 times the square root of 3/2 times 5/2. And that's going to give us 3.9. So a problem arises when we start talking about ions, and that's mostly what we have been talking about here, because ions are going to attract negative charges, whether those are negative ions or just the negative side of polar molecules, and those are going to form ligands. So ions generally have ligands, and that's going to move our orbitals around. So why does it move them differently? That's because instead of the electric charge being spread out evenly all around, it's coming in at specific points. And so it affects the orbitals that are close to those specific points more than those that are farther away. So how much they move and how they move is going to depend on how many ligands we have and what the geometry is. So right now we're just going to focus on octahedral arrangements because that's what we've been looking at so far. So this is a molecular orbital diagram of just a portion of the molecular orbital diagram of the interaction of a metal and of the 6 ligands that are in the octahedral arrangement. And thought I had a pointer here. Try this. Okay, so if I look at the left-hand side here, this is just an atomic orbital diagram for the metal. And these d orbitals here should all be at the same energy level, but we didn't have enough room to spread them all out. So they're just kind of pretend all at the same energy level here. Our s orbital is above the d's because it's an ion. So that's what happens when we ionize the metal, the s moves up. And then the p orbitals are above those. And then we would just fill this in the way we would fill in a normal atom or ion. On the other side, we have our ligands, but all we're showing here are these 6. And again, these should all be the same energy level, but we didn't want to write them all out to the side. These represent the 6 lone pairs that are pointed directly at the metal ion. And they form different combinations or salx that can interact with the different orbitals. And so when they interact, we get bonding orbitals down here, and then we get anti-bonding orbitals up here. Now, we've said that we're mostly concerned about what's going on here in the middle. So let me highlight that. So these are labeled as if they're d orbitals. They're really molecular orbitals, but we say they have d character. They're very close in energy to the d orbitals. And if we were to see their shapes would be very similar to d orbitals. Now notice these bottom ones here, the T2G, they really haven't moved at all. These are basically non-bonding orbitals. And it's really just the EG orbitals that have moved up in energy and are anti-bonding. Okay, so why is it that we only worry about these? So remember, our main concern is the frontier orbitals, the HOMO and LUMO orbitals. And so we're going to see how these are going to be our HOMO orbitals, or occasionally our LUMO orbitals. Our bonding orbitals down here at the bottom are going to be full, and they are going to be primarily ligand based. Okay, so mostly we just need to know that they're full, and so they're not doing anything interesting because they are below the frontier orbitals. So to explain this, let's look at an example. Let's say we take hexaaqua chromium 3+ ion. So we've got a chromium 3+. Its electron configuration is going to be Ar3d. Sorry, 3d3. And then we have our waters, and we're just looking at the lone pairs from the waters that are pointed at the chromium. They're going to be taking place over here. So remember that each water has a lone pair on it. So each of these orbitals is going to be filled with 2 electrons that are coming from those lone pairs from the water. So what that means is that when we start filling these bonding orbitals down here, they're going to be pretty full. All right, so we've got all 12 electrons here from the lone pairs. We place those, and then we've got our 3 electrons, our 3d electrons over on the left-hand side. Then we start filling from the bottom. So we put in our 12 electrons from our ligands, and they fill our bonding orbitals. And then once we're done with those, we start filling in the remaining electrons, which are just our d electrons, and they're going to go into those non-bonding orbitals that are the same energy. So it just works out that the electrons that were in the d orbital on, the d orbitals on the metal stay in the orbitals of d character, and that's always going to be the case. So these are always going to be our frontier orbitals. Okay, so what are we going to do with this? We are going to have a situation where we might have different numbers of electrons. We were looking at chromium 3+. Now let's take a look at chromium 2+. So chromium 2+ has 4 d electrons. Where are we going to put that 4th d electron? So we have a couple of options. One option we call low spin. We're going to take that extra electron shown here in red, and we're just going to put it in the bottom. We're going to pair up with one of the electrons on the bottom. So the advantage of this is we're not putting that electron in a higher energy orbital. Things like to be low energy, that's the most stable. But the disadvantage is we're pairing the electrons. And remember, when the electrons are in the same orbital, we've got that pairing energy that destabilizes them. So those two things are working against each other. So again, we call this option 1 low spin. All right, option 2, and this first 2 bullet points, same information as on the last slide. Option 2 is high spin, and that's where we take that last electron shown here in red, and instead of pairing it, we put it in the EG orbital. So the advantage of this is we don't have that pairing energy, but the disadvantage is now we're populating the higher energy EG orbitals. Okay, so we've got a little bit of conflict going on here. So how do we know which option is appropriate? So here's our 2 arrangements. And so why do we call them high spin and low spin? If we were to calculate the spin by the number of unpaired electrons divided by 2, we would find that for the low spin environment, we have S is equal to 1, and for high spin, S is equal to 2. So this is always going to be the case. If we start populating the EG orbitals, we'll get a higher number for S than if we fill up the bottom T2G orbitals first. Now, something else to notice, and we'll keep coming back to this, is the spacing between T2G and EG. So between these 2 on the left-hand side, on the low spin side, this is a pretty big difference. But when I go to the high spin, it's quite a bit less. So I decrease that distance, all right? And we'll look at why that is here. So what determines if a complex has low spin or high spin? That difference there in energy is what's going to make the difference. and we use the symbol delta O for the energy gap, and that is sometimes also called the splitting energy. Now the O here stands for octahedral, and that's because we're going to have a different sort of arrangement whether when we have tetrahedral or when we have square planar. So this arrangement is just for octahedral. And we sometimes refer to this as the field splitting or the crystal field splitting. So we're going to look at the balance between this gap, the crystal field splitting, and the energy required to pair the electrons. So if it's one electron that has to be paired, then we just have one pairing energy. If we have multiple ones on the bottom, we'd have to consider, then we'd have multiple pairing energy. That is labeled with a capital P in Greek, or pi. So if the splitting is larger than pi, then the complex is low spin because the energy gap is too big for the electron to go to the higher orbital. If delta O is smaller, if the crystal field splitting is smaller than pi, then the pairing energy is too big to allow the electrons to be paired, and the electrons are going to spread out as much as possible. All right, so this kind of summarizes what we just said. If delta O is greater than pi, we have low spin. If delta O is less than pi, we have high spin. All right, so how are we going to know when we're going to have low spin or high spin? Well, we already know that for low spin, we're going to have a larger delta O. This can happen based on where the element is. So if I have a first row transition metal, those are smaller. And the smaller the ion, the more likely I am to have a small splitting. Okay, with my large ion, I tend to have large splitting. So my second and third row, we're going to pretty much assume are always always low spin or large splitting. Now for the first row, our elements that we're most familiar with, the iron and nickel and cobalt and manganese, these, it's going to depend on some other factors. And so one thing that it's going to matter is the charge. Now, if I have a high charge, that's going to draw the ligands in closer to the metal, and the closer they are, the better the orbital overlap. If I've got good orbital overlap, that means that I'm going to move the orbitals more. And that means that I have larger splitting. But if I have poor orbital overlap because the charge is low and the ligands aren't drawn in as close, then I'm going to have a smaller spacing. Now, this is going to depend on which metal it is. So we can't always say this number is going to be high spin and this number is going to be low spin. But if I'm comparing to, the higher charge is more apt to be low spin. And the last thing, which we're going to focus more on here, is the ligands themselves. And so if we have ligands like carbon monoxide and cyanide, they tend to be low spin. You can pretty much guarantee you'll have a low spin scenario there. And if I have ligands that are halides, chloride, fluoride, bromide, those are going to be high spin. So we'll see why that is here in just a second. All right, so on the handout that I gave you in class on Wednesday, you should have had this picture here on the left. So the free ion is imagining if our ion, let's say the vanadium 3+ or 2+ that we were looking at the very beginning, was just floating out in outer space and there was nothing around it. Then there would be nothing affecting the orbitals relative to one another, and there wouldn't even be any negative charge around. And so all the orbitals would be degenerate energy. Now, if I did have a negative charge, but it was coming equally from all sides, that negative charge is going to increase the overall level. So we call this the Berry center, where the orbitals would be if we had a spherical field. Now, that's not a realistic situation. We don't actually have spherical fields because the electrons or the negative charge has to be coming from somewhere. And so usually it's arranged in an octahedral field or a tetrahedral field or something like that. So in an octahedral field, the orbitals split relative to this Berry center. Okay, so the T2G goes back to where it was as a free ion, so it's non-bonding, and the EG rises up in energy. And you'll notice that the Berry center isn't exactly in the middle. The difference is based on how many orbitals there are. So if I take 3 times this 0.4, then I should get 1.2. So I've got a total of 1.2 below the line. And then I've got up above it 2 orbitals that are 0.6. So 2 times 1.6 is also 1.2. So it balances out that way. Okay, so we are going to use those numbers in a minute to find crystal field splitting energy and or stabilization energy. This is also called ligand field stabilization energy. Technically, they're slightly different, but we're going to use those terms interchangeably. So to look at why we are looking at this, this is one of the data tables from your book. And so what we're showing here in black is where we would expect a trend line to fall for the different number of d electrons. We would kind of expect that the more d electrons that we have, we would lower our enthalpy of hydration at a pretty steady rate. But what we find is there's at first a very quick drop off, and it's kind of linear, but then it levels off and comes back up, meets where that line would have been before, then drops off again and then levels off. So why does it do that? And so this has to do with the stabilization energy. If we put in a correction for the stabilization energy, so the open circles are where the actual data points lie. If we correct for the stabilization energy, then we get these black points that are right where we would expect them to be. So let's see how we figure out what that stabilization energy is. So the formula is to take the 0.6, that was the difference between the Berry center and the top, and multiply that by the number of electrons that are in the EG orbitals. So this is EG, and this, and then the E is electrons. Okay, so EG orbital, and those are electrons. And then we're going to subtract off 0.4, that was the difference between the Berry center and the bottom orbitals, and the number of electrons in the T2G, and that E shouldn't have been subscripted. Sorry about that. So all of this is just a factor that gets multiplied by the delta O. So really I ought to have delta O over here, but again, it wouldn't fit on the screen. So delta O goes over here, and you'll see that appear on the slide in just a second. So let's do an example. If I have a D3 metal, I have 3 electrons. They're going to go in the T2G orbitals. And so there are no electrons in the EG orbitals. There are 3 in the T2G. And so I just plug those in. 0.6 times 0 minus 0.4 times 3. And that's going to give me a negative 1.2. But the negative 1.2 isn't really negative 1.2 joules. It's negative 1.2 times whatever the difference in energy between those orbitals are. So times delta O. So our stabilization energy is negative 1.2 delta O. Okay, so let's look at another case. Let's say we have 7 electrons. So we can arrange those 7 electrons into the orbitals like so. So let's see if you can figure this one out. I'll go through this slowly, but you might want to stop the video and see if you can determine this without seeing the answer. All right, so we end up with negative 0.8 delta O. Okay, so notice we have more electrons, but our stabilization went down a little bit. Instead of 1.2, we have 0.8. And this is because we have the EG electrons that are kind of destabilizing the situation here. So the more electrons in the T2G, the more stable it is, the more in the EG, the less stable it is. So this kind of begs the question, well, what happens when we have this as a low spin scenario, which is going to be more stable, high spin or low spin? So we see high spin here, but one of these electrons that is on the top could actually be down here paired up with this. So let's take a look at what that situation would be like. So again, you try and calculate what the crystal field stabilization energy would be. You might want to stop the video, and I'll go through this slowly, and you can see if you got the right answer. All right, so in this case, we get negative 1.8. So this is the largest that we've seen so far because we have a whole bunch of electrons on the bottom and just one on the top. So the most we could have is if we had 6 electrons on the bottom and nothing on top. But if we have equal numbers on top and bottom, it should work out to 0. So it should always either be 0 or negative. All right. In our low spin case, even though the spin is less, the stabilization energy is more. It is more negative, more stable, having more electrons in that T2G orbit. All right, so let's take a look at when we might have different kinds of interactions from different kinds of ligands and how that might change those T2G orbitals. So far we've said they pretty much are non-bonding, but that's not always going to be the case. So all ligands are sigma donors or sigma bonders. And so for the octahedral arrangement, we can see the sigma interactions with our EG orbitals. So on the far left, we have, this is a lone pair coming from a ligand. This is a lone pair coming from a ligand, and they're coming in onto the DZ squared orbital directly. So we get nice overlap, good overlap there because they're pointed directly at it. And then around the sides, I can get the other orbitals coming in and interacting. Now I'm showing the bonding sense here. So these would end up being more ligand-like in character. If I swap the shading of the metal orbital, then I would have the anti-bonding sense. So the anti-bonding d orbitals are going to be very high in energy. So normally we say that because the bonding ligands or the bonding frontier orbitals are pointed directly at the EG orbitals and not at the T2G orbitals, we say that T2G are non-bonding. But some ligands have other nearby p orbitals. So if I take something like a halide, chloride has 4 lone pairs. And so there are p orbitals that have lone pairs in them that aren't participating in the sigma donation. They're not part of the adduct, but they're still there. And so when I get this interaction between these, I'm going to get some that's kind of a weak bonding sense. That's just going to lower the energy of the ligands. And then if I swap the signs on the metal, then I'm going to have the anti-bonding sense. Well, that anti-bonding sense is for this type of orbital, and this is a DXY, which is one of the 3 T2G orbitals, the others being XZ and YZ. So each of these, instead of being non-bonding, can be slightly anti-bonding. So why is it slightly? Well, this is a pi interaction. They're not pointed directly at the ligands. And so it's weaker because of that. So we get a slight interaction that raises up those T2G orbitals just a little bit. Well, if I'm raising the bottom orbitals, the spacing becomes smaller. And so this is why sometimes we have ligands, such as the halides, that are going to have weak fields or small splitting between the T2G and EG. So this happens whenever I have more than one pair of electrons on that ligand atom. So our halides and things with oxygen in them are the most common scenarios. So oxide ion, hydroxide, water, and just the oxygen molecule. So that's because there's an extra lone pair or multiple extra lone pairs that are irritating the T2G orbitals and raising them up in energy. Okay, we call this type of ligand a pi donor ligand. It is also a sigma donor because they're all sigma donors, but these are classified as pi donor because in addition to being sigma donor, they also donate a little bit of pi electron density. Our last group is what we call a pi acceptor or back bonding orbital or ligand. And so good examples of this are either carbon monoxide or carbon dioxide. So looking at the left-hand side here, we can see the sigma donation. Here's the metal. They're showing a p orbital, but it could also be the DZ orbital if this were on its side, or the x squared minus y squared orbital. Could be any of those. So this comes in and we have the lone pair here coming off of the carbon interacting here. So when this interacts in a bonding sense, that has the character of the ligand, and the anti-bonding sense where these are flipped, that would be more like the metal. Okay, so this is what we normally think of as the sigma interaction. But now let's think for a moment about what about this carbon monoxide molecular orbital diagram by itself before it ever came to the metal. All right, so this is just a diagram of the carbon monoxide. So over here is carbon, on the other side is oxygen. So this is not involving the metal at all. So we have the bottom part where we have the s orbitals overlapping, and the top part where we have the p orbitals overlapping. And we've got three nice bonding orbitals here. One of them is sigma and two of them are pi. And so this sigma one here is our HOMO. And then right above it is the LUMO, the lowest unoccupied molecular orbital. And this is what we're going to be interested in. So important thing to remember here is, first of all, that it is pi. So pi bonds have B symmetry, and also that it is empty. There are no electrons there. All right, so now let's go and take this back to the metal and see what's going on when this interacts with the metal. So for our metal, I have the dx squared, or I'm sorry, the dxy orbital or the dxz or the dyz orbital that has this shape. And then for my ligand, my carbon monoxide, this is my LUMO, the anti-bonding pi. So it has the B symmetry in that the top and the bottom are opposite signs. And then it's anti-bonding because between the two atoms, we change shade. So we go from not shaded to shaded, or from shaded to not shaded, crossing between one atom to the other. So that's why it's anti-bonding here. But when I bring this up against the metal, these may have like arrangements. Now before, we would call the bonding scenario more like the ligand, but in this case, the ligand orbitals are empty. This was the LUMO, the unoccupied one. So when they interact, this doesn't have any electrons to give, but our metal, on the other hand, where does it put its electrons first? In the T2G orbitals. And this is one of those T2G orbitals. So if I'm talking about a D3 metal, it's got an electron in here, and it can donate some of that electron density back to the carbon monoxide. So it's called back bonding or pi acceptor because normally we talk about the ligand donating to the metal, Now it's going backwards from the metal to the ligand. So the ligand is accepting a little bit of electron density. So what happens then? Our carbon monoxide gets weakened. Why? Because we're putting electron density into this antibonding orbital. Okay. So the bond is less than a triple bond. It's more like a double bond, not quite double, but somewhere in between. There is a less electron density in the metal antibonding orbital due to that stronger metal ligand bond. And the ligand is drawn closer. So instead of having this negative charge here that's repelling the lone pair, that negative charge is moved back over to the ligand. And so this whole molecule can get in closer. The closer it gets, the better the overlap. The better the overlap, the higher those EG orbitals are. Okay, so the EG orbitals go up in energy, but the T2G is stabilized and those go down in energy. So we get a nice big splitting gap in between the two. All right, so pi acceptor ligands include ligands that have double bonds, like carbon monoxide or triple bonds, carbon monoxide or cyanide. Now, this wouldn't work the same way if I had electrons that were filling those upper orbitals. So kind of has to have a pretty specific scenario. If I already had electrons there, then it'd be harder to put the electron density from the metals. This molecule on the right is phenanthrene, and then the nitrite, which those of you in lab have worked with that, and then the thiocyanide ion with the nitrogen attachment. These all can serve as pi acceptors, and so they're going to have that big splitting. All right, so let's put all of this together here. We can organize our types of ligands by the kind of bonding. This is called the spectrochemical series, and we go from strong ligands to weak ligands. Our strong ligands are the pi acceptors. Our weak ligands are the pi donors, and the ones in the middle are sigma only donors. So they don't do anything with pi. The stronger the ligand, the greater the splitting. The weaker the ligand, the less splitting we have. Okay, so we call them strong field and weak field, and then the ones in the middle we would call midfield. Now notice for our midfield ones, we have the ammonia has a nitrogen, ethylene diamine has nitrogens. Here we have a nitrogen on the NCS. So these are going to be our midfield ones. Okay, and that's because typically nitrogen will only have one lone pair, and therefore it doesn't have the interactions of the other electron, other lone pairs. So when we have a strong field, we're likely going to have a low spin arrangement because we have greater splitting. When we have a weak field, we have less splitting, so we're likely going to have a high spin environment. All right, so obviously this is going to affect magnetism because it changes the number of unpaired electrons. So if we consider iron 2+, this is a D6 ion. When I don't have any splitting at all, so when I have a free ion floating out in space, the spin is 2. So this is if I have all of my d orbitals are the same energy level. If I have high spin, it's going to look something like this. My spin is also going to be 2. So I have 4 unpaired electrons. Half of 4 is 2. But if I have a strong field ligand, that's going to separate my orbitals. And so the top electrons are going to drop down into those T2G. And now I've got everything paired up in a low spin environment with a spin equal to 0. So sometimes we can have iron compounds that have no magnetism or that they are diamagnetic. All right, so let's talk a little bit about some other shapes. The tetrahedral environment is a little bit different from the octahedral environment because of the way the ligands come in. So here we have a cube. We can think of a tetrahedron as being formed by having ligands at 4 of the 8 corners of the cube, and they're going to be in a staggered arrangement. Now remember that for our orbitals, the dz squared is going to come up and down into the faces at the top and the bottom, and there's no ligands there. And then our x squared minus y squared are going to go to the faces along the y-axis and along the x-axis. And again, we don't really have any ligands there. So these orbitals are EG orbitals, which are no longer Gerata or Ungerata because we don't have an inversion center. So we're just going to call them E. Our E orbitals don't really move a whole lot. In contrast, our T2 orbitals, again, no longer Gerata because we don't have an inversion center, they're going to come out to the edges. So the lines connecting the corners. Now we don't have we don't have ligands sitting there, but we've got them pretty close by. So if I'm looking at this lobe of the d orbital coming out here, there is a ligand close by. So the fact that it's not pointed directly at it means that this effect is going to be less. Okay, so we're going to see less movement, but it also means that we're going to see movement in the dxy, the dxz, and the dyz. Those are our T2 orbitals. Okay, so let's take a look at what that means for our orbital picture. So the ligands are not pointing directly at any d orbitals. So the effect on the orbitals is less. That means that from the barycenter, they move less. So that's less splitting. And the ligands are closer to the T2 orbitals. So the T2 orbitals are going to move up or destabilize more than the E orbitals. So the effect of this is that for a tetrahedral environment, we get 3 orbitals on top and 2 orbitals on bottom. So octahedrals on the left, this is what we've normally been talking about, 3 on the bottom, 2 on the top. Okay. Tetrahedral is on the right, and we have 2 on the bottom and 3 on the top. So we've swapped positions. Notice also that for the tetrahedral, they're a lot closer together for the TD, and for the octahedral, they're farther apart. And that difference of this delta with a little t means the splitting for a tetrahedral. That's 4/9 of what it would be for the octahedral. So about half of the distance or the energy difference for the tetrahedral as compared to the octahedral. And that's going to mean tetrahedral usually has a small enough splitting that it's going to be a high spin environment. All right, so that gets us to the end of what we are going over. And you have a homework assignment that is listed on Canvas. So take a look at that, and that includes doing some vocabulary for chapter 10.